All right, now that you understand the shapes, molecular geometry, why do we care? So if I have myself a molecule, generic atom X, and the generic atom X is bonded to let's say oxygen, these guys are going to duke it out. Okay, they're going to duke it out for who gets to control the electrons more, and that's based upon their electronegativities. So let's say oxygen is more electronegative than X. So what ends up happening is the electron density is going to spend more time around oxygen than it will X. In effect, this side will then be a partially positive side, and this side will be a partially negative side. What we'll say is this molecule, therefore, experiences a dipole moment. So we're going to draw an arrow like that. Positive over here, negatives going this way. So we're going to say that this guy has a dipole moment. Dipole, di meaning two, pole, two poles. Well, why does that matter? Comes along another XO that's having its own dipole moment. This side is partially negative, this side is partially positive. It is having its own dipole moment. Now, what's going to happen? This guy has its dipole moment, this guy has its dipole moment. Well, what do we know about law of electrostatic forces? It's like a trend. We keep saying over and over and over again, opposite charges attract. And so what we're going to get is we're going to get some attractive forces. Now, they might not marry up like this. It might just be this X is coming over here like a this. All right, but this has a partially positive, this has partially. So we're gonna have attractive forces. It doesn't have to be both of them. And so what we're gonna say is there is a dipole to dipole or a dipole-dipole attraction. This is a type of intermolecular force. Now, just like with all charges, Q1 times Q2 divided by radius squared times a constant is going to be equal to the force of attraction. So of course, the bigger the charge difference, the bigger the force of attraction. So if this was replaced, let's say with fluorine, and this was a bigger partially negative, and this was replaced with fluorine, this was a bigger partially negative, and resulted in a bigger partially positive, well then we get a stronger dipole-dipole attraction. Now, with that being said, if you have hydrogen with its one single electron right here, hydrogen with the one single electron here, and if it bonds with an element over here, let's say fluorine, okay, most electronegative element, it bonds with fluorine. Well, when they share, fluorine says, hey, I will lend you my electron, you lend me your electron, not really, of course, and we're gonna share these electrons. Fluorine, being so electronegative, basically takes all of the negative charge and holds it around it. Now, the hydrogen still gets kind of a taste of it, and so it's not ionized. The hydrogen's not completely ionized. It didn't remove it and form an ionic bond, but what it did was it created a very big partially positive. And why? Because hydrogen is just a proton with an electron. And if the electron is taken over here, that essentially leaves a naked little proton over here. Now, what does that mean? We've got a very big partially positive, a very big partially negative, and when it comes in contact with another one that's done the same thing, here's my hydrogen, and here is my fluorine over here, and we've got a very big partially positive, it looks like a dipole-dipole attraction again. And it is, that's another dipole-dipole attraction. However, because it's really, 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 really strong, it involves this hydrogen being a naked little proton, we call it hydrogen bonding. Hydrogen bonding is really nothing more than a very strong dipole-dipole involving hydrogen, bonded with fluorine, bonded with oxygen, or bonding with nitrogen. If it's one of those three guys, those guys are very electronegative. It pulls a very big partially positive, partially negative dipole moment. And then the attractive forces between these are undergoing hydrogen bonding. Now, it seems like, well, why differentiate that? Once again, we talked about it in a previous video, one of the glues of all of life are things like amine groups. We've got amino acids and stuff. You can see that you have a very big nitrogen, hydrogen there. We have things like hydroxyl groups. And these guys right here, these are all glues being held for like organic chemistry, biology, etc. Lots of molecules, like not so much fluorine, but nitrogens and oxygens, they make up the backbone of so much of what is biology, what is organic chem, and so much of what's actually happening. And so these are very special little fellers here that are gonna go ahead and create a lot of intermolecular force attraction between big molecules, between macromolecules. And so with that, big attractive forces creates glue. And it creates, like, why does DNA? Why does DNA zip and unzip? Well, we have attractive forces going in there. Then we have something that comes in that kind of usurps that attractive force, takes over the attractive force, and so now it unzips. And why does G go with C? Why does A go with T, etc.? Well, in DNA. And that's because of the way it's like a lock and key mechanism. These guys fit in a certain way based upon these positives marrying up with a negative in a certain way that only a certain orientation of them will actually fit, kind of like a puzzle. So we have dipole to dipole attractions. We have hydrogen bonding. You might, like, you can even put in like water. So water, of course, water. We've done it in class a whole bunch of times. Water, partially positive, partially negative. When water bonds with other waters, hydrogen bonding. But we also know water can grab hold of metals on the negative side, and the non-metal, that this metal chloride, this ionic compound. So this is, let's just say, okay, this is sodium ion, this is chlorine ion. Positive charge, negative charge. It's put in water, water comes by. Well, that adhesion that's gonna happen, that negative to positive ion and that positive to negative ion is actually the dipole of hydrogen, which is hydrogen bonding with all the other waters, creating what we would call a dipole ion or ion dipole attraction. And so, you know, you can kind of look at things like that. Ion dipole attraction, the dipole of water bonding with the sodium positive side over here, that's an ion to dipole attraction. And this is what causes them to dissociate. We're gonna come back to London dispersions in a bit. We'll do it in another video. But that's basically in a nutshell what's going on there.